Hi everybody, welcome to another video in this quiz math section 1.8 proof methods and strategy. Just like last section is kind of like the introduction. If you haven't seen proof before, this might be difficult, but we'll just go over some cases, and after some practice then you get familiar with some of the technique that we can use to prove. But usually when we try to prove something, that's a very creative process, and because sometimes it takes a lot of practice to be creative as well, and this indeed is the case. Right, so the first one we call the exhaustive proof or proof by case. So if we can list all the cases and we verify that every single case it works, then that is a proof. And usually that's not a very good technique because sometimes it too many cases to consider. Right. To prove the conditional statement, for this one, if we rewrite this, we can say if we want to prove each one of that is true, then we can just need to show one of this. I mean, this is the conjunction to have to show every one of those is true. So for example, let A add B, meaning that we find the max number between A and B. Right. So max number of A and B is equal to A if A is greater than or equal to B. So that's what the max function does. By the way, in computer science, if you want to write the max between A and B, there is a way to do that. We can use absolute value of A minus B, and then plus A plus B divided by 2. So with that, let's look at some example. Let's say we start with 5, which is bigger than B. So that is 3 plus 5 plus 2, so that 10 divided by 2 is 5. So that is the bigger number of the two, right? Now, I say, what if we put that backward? Well, if we put them backward like this, 2 minus 5 is minus 3, absolute value is minus 3, we still have 10 divided by 2 is 5. So it doesn't matter what number we put. No, wait. Put it backward, did I? Right, so that 3 plus 2 plus 5 divided by 2 is 5. Yeah. So it doesn't matter where we put it. It will give us the maximum number. Right. So that's good. However, when there's 3 numbers, we cannot really write something. It will be a lot more complicated than this. So in that case, let's just look at different scenarios. So we suppose A greater than equal to B greater than equal to C. Case number 1. Case number 2, we can say A greater than C greater than B. So we done put an A first. Now how about put B first, and then A and C, and then B first, and then C, and then A. Finally C first, and then A, and then B, C, and then B, and then A. Right, so those are 6 cases. Of course, we can just show each one, but that will be repetitive. All we need is just one case, and then the rest will be done similar. And that brings up to the point we'll try to make in the next page. Just pick one. How about we choose this case? Right. Now the left hand side, equal to A at B at C. Now, because A at B is bigger than A, so this is equal to B, because B is bigger than A. So this is equal to B at C. Now between these two, B is bigger than C as well. So this is equal to B. So left hand side is equal to B. What happened on the right hand side? The right hand side is A. A at B at C. Right? Now, do inside the parentheses first. Once again, we assume B is bigger than C. So this gives us B. And that gives us A at B. Now A at B. B is bigger than A, so that ends up being B. So left hand side equal to the right hand side. So that's why, that means it's true. We need to prove it with 6 different cases. And of course, will be proved similarly. So we said similarly done. Or all the 5 cases. There's a better way to write this, but for now we just say all the 5 cases can be shown, can be proved. So we prove for all the cases. So that's why this is true. Right, associative proof. Sometimes theorem can be proved by examining relatively small number of cases. So in this case, something like this. Prove that when n is the positive integers less than or equal to 4, then this is true. So less than or equal to 4, meaning that n can be 1, 2, 3, or 4. Right? Only 4 cases. So case number 1, n equal to 1. If n equal to 1, we put in here 1 plus 1 square. Is that greater than 3 to the 1? Right. 1 plus 1 square is 2 square. That is greater than 3. So that checks. So case number 1 is good. Case number 2. When n equal to 2. Put 2 in for n. So 2 plus 1, 3 square. And that is greater than equal to 3 square. So that also true. They equal, but still true. Case number 3. N equal to 3. Right, n here, right, so 3. So 3 plus 4 square. Right. And that's a cube, right? So this is not true. So for that, we say this is not a theorem. So I should say that very fine. That is the case. Of course, if we put 4 here, that 25 and that 3 to 4 is not greater. So that's why this is not a theorem. And so in that case, let's change the question. That proof, instead of proof, we said check to see if, and in this case it is not. Right, but I'm just going to go over all the cases. Right. Now, without loss of generality. So this is what I prefer earlier. So instead of saying similarly all 5 other cases can be proved can just say without loss of generality, assume that b greater than equal to a greater than equal to c, and then of course we know the other cases can be handled similarly, so we don't have to do that. So the without loss of generality is a very common term in math. Right, let's look at this proof. Show that if x and y are integers, both x times 1, x plus y are even, then both x and y are even. Right, so did we see something like this before? Right, so what we see is, if we say it, we go from x times y, x plus y to something simplified, that's more difficult. It will be easier if we use the contrapositive. So let's just go with contrapositive here. So both x and y are even. So we said if both x and y they said both and not even, then xy and x plus y are again not even. Of course the key word here have to be both. Right, so now if both of them are even, that's easy. What if it means both of them are not even, meaning that one of them has to be odd. So both not even, meaning one, at least one is odd. Right. Now, if we say at least one of them is odd, so we say it could be x, could be y. So in that case, that's what the word coming in. We say without loss of generality, meaning that. So we say let x be odd. Like I said, one of them has to be odd. Of course, both of them can be odd. But let's say if x is odd, and now let's suppose case y is even. Right. So in that case, x is odd will be 2k plus 1, and y is even, let's say 2m. Of course, m and k are any integers. So let's do quickly x plus y, 2k plus 1 plus 2m. Of course, we can factor out the 2, m plus k plus 1. And of course, that is odd. So that satisfies that both of them are not odd. So that's good. How about x times y? Uh, 2k plus 1 times 2m. Well, this is even because there's just a 2. It doesn't matter. One of them is odd, so that means not both of them are even. So that's okay. I mean, in general, so that check. Not pronounce space here, but we do need to say still let x be odd. But now this time, suppose y is even. Suppose this time y is odd as well. and we continue in this node part. So that x plus y, again 2k plus 1. In this case, y is equal to m plus 1 because they y is odd. So when we add them, we have 2k plus 1 plus 2m plus 1. So that is to factor out the 2, k plus m plus 2. K plus m times 2, anything times 2 is even, plus 2 is even. That's not what we want, but how about the product? So multiply out 2 times 2, that's 4. For mk plus 2k plus 2m plus 1. So we can factor out the 2. Factor out 2, here we have 2mk plus k plus m plus 1. Now the long one here makes that as an odd number. So yeah, so one of those is odd. So that means not both of them are not odd. So meaning one of them is not all of them, not both of them are even. Meaning at least one of them is odd. So this case that this time is odd. So we cover the both cases when y is even, when y is odd. But we assume that x is odd. Of course, we said without loss of generality, if y is odd, we can do the same thing. So that's how the proof go, right? So when we write like this, we don't have to assume that the case when y is odd, because we prove the same way. Right, so that is the first proof. We will look at all the different scenarios. And the next one is existence proof. Now this will be very difficult. Sometimes we just have to find something that will work, and depends on problem. That will be a very difficult thing to do. So there are two types constructive proof. So either we find an element that will work, or we find a different way that even though we cannot construct that, but it might work somehow. Right, we'll see that in a minute. Right, look at the first example here. Show that there is a positive integers that can be written as the sum of cubes of positive integers in two different ways. Right, so we have to go up to this number to see there are two different ways there. Right, so that's good. I said if we found one example, that's good, because this is proof for existence. If we can find one, that's good. Right, next, show that there exist irrational numbers x and y such that x to the y power is rational. Now this is a little bit difficult. It's the classic problem. So let's see. Right, now we know earlier square root of 2 is a rational number, right? So fact, square root of 2 is irrational. Right. And then my question is, what is square root of 2 to the square root of 2? Is irrational or not? Right, and then it will show that it doesn't really matter. And that's the point here. Right, now in that case we'll consider two scenarios. So case number 1, suppose this is irrational numbers. In that case, let x be square root of 2 and y be square root of 2. So x to the y is square root of 2 to square root of 2, and by the assumption it is irrational. So that's good, because we assume that it's good. And then you say, what if it's not? Well, I'm glad you asked. Is wait, sorry, I got backward. Okay, suppose that is rational numbers, so that is rational numbers, so that's good. Irrational numbers raised to irrational numbers is rational, right? So sorry, it should be like that. Suppose it's rational numbers, then we have irrational number raised to irrational number equal rational number. So we found one example that show that they exist. Now, if it's irrational number, if it is rational numbers, so if it is rational numbers, so that let x be that. And then we choose y, the square root of 2. Now we assume that it is irrational numbers. This is irrational numbers, so we have both of them irrational numbers here. So what is x to the y? X to the y is 2 square root of 2, 2 square root of 2. Power to another power, we multiply them. There. So this is rational numbers. So even though we're not sure if this is a rational number or not, but there is a construction using that number to make it into a rational number, right? So even though we did not prove it, so this is we did not prove it directly, but we can show that there this one exists one way or another. Like that, it is the classic proof. So it requires classic solution as well. Right, so that proof for existence. Next proof is for the uniqueness. For uniqueness, we have to show that it exists and is unique. Right. Now let's say so that if a and b are real numbers and a not equal to 0, we can prove that. Right. Now let's focus on the uniqueness part of it. To prove that it is unique, just say if y is not equal to x, then y does not have the properties. Right. So that there is a unique number r such that a r plus b equal to 0. Right. So like I said, there's two parts of the proof. The first part is existence. So if we start with a r plus b equal to 0, and we show that there exists number r, right? So we can show for r, a r equal to negative b. So r is equal to negative b divided by a. Since a not equal to 0, that number exists. Let's check. Now we prove uniqueness. For uniqueness, suppose they are both of them. Suppose there 2. Of course, they have to be different, otherwise it could be unique, right? So we assume that they are different. Now, because suppose they are both of that such that suppose both of them works, suppose both of them work. Now since both of them equal each other, both of them equal to 0, so why don't we make them equal each other? And we can subtract b on both sides. And then divide by a on both sides. So R1 equal to R2. Of course, that contradicts to what we have earlier, right? So this is proof by contradiction. So that means the R are not unique. I mean, that means the number are unique. There's no other option. There's only one of them that works. If there are two of them works, those two are the same. So it's unique, right? So, yeah. So it is unique. Because if two of them work, they are the same, meaning they're unique. Right, proof strategies. Like I said, usually when we try to prove things, this is a creative process. And definitely it takes a lot of practice to get to develop some kind of strategy. And of course, either direct proof or indirect proof. And here's some other proof that we can try. But like I said, it needs some practice and a lot of creativity. Right, so let's look at this kind of nice example. This application in tiling, meaning that we try to make it like Tetris game, try to fill out something with some certain pattern. We just look at this particular example. The question is, if we have the chessboard like this, or I call the checkerboard, or actually the chessboard, can you put domino on it so it will cover the whole board here? And the answer to that is yes. If you can just put 2, 2, 2, 2, 2, 2, and 2, and just line in column, you will fill out this one easily. So the answer is yes. Yeah, just put each of them stack in this pattern, and we just keep going that for the rest of the board. So that's easy. Next, can we tile a checkerboard obtained by remove one of the 4 corners? So now, if we just remove one corner, how many squares do we have left? Originally, the checkerboard or the standard chessboard is 8 by 8, so 64 square. Divide by 2, so that certainly works here. Now, if we remove one corner, meaning that we have only 63 square left, and each domino only fill 2, there's something left. There had to be something remain, right? Meaning one square is left uncovered. Right, so that's easy. If 63 and we have on the dominoes, each domino can only cover 2, so they have 1 left because it's an odd number. That's easy. Now, how about if we remove the 2 corners? Can we still fill with the dominoes? Then first we think, well, 64 if we remove 2 corners, we have 62. And each domino can cover 2. So the answer should be yes, right? Think about that. Now we remove 2, so we have 62 square. And each domino cover 2. So can we cover every square? Or can we tile it? Of course, the answer for something like this should not be yes. Because if it's yes, that's obvious, right? So what is the deal here? Now, think about when you tile, when you put the domino, doesn't matter how you line up. Each domino can only cover 1 black square and 1 white square. Doesn't matter how you line up. Each domino can only cover 1 black square and 1 white square. But if we remove 2 corners, opposite corner like this, both of them are white. So this 62 square, 30 of them are white square because we remove 2 out. And 32 are black square. Right? Remove 2 corner white square here. So in that case, we still cannot cover every square with the dominoes. Unless we break a domino in half, then we can do that. But that's not the point. Because each domino cover 1 black square and 1 white square, we have an uneven number like this, it will never work. So the answer is no. Because each domino cover a black square and a white square. So that's why it did not work. Right. Now something even more interesting. Let's say if you have the chessboard and you have a knight like horses, the horse piece. Can we travel every square? And when we stop, at the square that we stop will be the new one. So we will not repeat it, the step. So meaning when we go, when the knight move, it will go travel everywhere on that and stop one time. I mean, each square, it can only stop at one time. It cannot go back to that. And we still have the same chessboard here. Right, the answer, can you do that? Well, let's look at the move of the knight. If you're not familiar with chess, the knight move, let's say if it start here, it will go up and to the left, or you can go up to the right. Of course, you can go down to the left or down to the right. So let's say if it start here, it can go 1, 2. So it can go here, 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 and here. So 1. So straight and then up, and then straight and then diagonal. Doesn't matter where it goes. Now notice that if you start here, you will go to all the black square around. So just like the last one, the move of the knight, if it start from a black square, it will end up at the white square. If it start from the white square, it will end up at the black square. So it's just alternating like that. Because it's alternating like that, we have an even number of white square and black square. We cannot move the knight in such a way. If we stop, it will travel each square once. So the answer is still no. Because each move the knight alternate colors. I should say the the square where stand change the color every time it move. But of course you get the idea. Now if change color like this and we have uneven number of white square and black square, it will not work. It have to be even for that to work. Actually, not be the case. If it is 30 and 31, it may work. But it is 30 and 32, it will not work because there are two more. Cannot make up for that. Think about this. If that we can go like even, I mean black, white, black, white, black, it's still okay, right? But if there are two more than the other, it will not work. Doesn't matter how we played it. Right. Now on the final note, like I said, proof is hard. Sometimes we have no solution, and this Feynman's last theorem, it says that there's no solution for n integers. We have x to the n, y to the n equal to z to the n when x, y, z not all equal to 0. Pretty much we have all of number integers, and so that there's no solution when n greater than 2. And the proof is very difficult. That's why it takes over 300 years before it is proven. Right, and other method proving. Right, I just want to say that what we covered in the videos, this one and the previous one, are just some of the basic technique. To prove something, it takes a lot of practice, and it takes even more creativity to actually prove something. But that's all we start. That's all we cover for these two sections. I'll stop here. As always, thank you for watching, and see you in another video in this week, man.